Swayam Prabha. Digital India. Educated India.
Welcome to the class of Physical Chemistry 1, and I'm Dr. Amita Pathak Mahanti. I'll be offering you this course. So this is an introductory course to the classical chemical thermodynamics. What we are going to do today is do the basics of definitions of thermodynamics, and then do a bit of mathematics as to what is exact and inexact differential, because that is what will be the basis on which the entire thermodynamics, whatever we are going to discuss, is going to stand on, and also to distinguish between a state and a path variable based on the partial differentials. So to start with, let us go with the primary goal of thermodynamics. In thermodynamics, we'll be always dealing with the equilibrium state. So it is to determine the equilibrium state that eventually results when a system undergoes a change in state, and also to quantitatively study the energy transformation associated with any physical or chemical process. And what does it offer us? It offers us, thermodynamics offers us a framework for relating the macroscopic properties like the pressure, volume, and temperature of a system to another based on some fundamental laws. And the purpose of studying thermodynamics, why it's so important? It is actually to harvest energy from different sources. It gives us information as to how much and to what extent we can harvest energy from different sources. So thermodynamics is basically divided into three types. One is the classical chemical thermodynamics, one is the statistical one, and the irreversible one. What we are going to discuss today and for the entire syllabus is the classical form of chemical thermodynamics. In the classical thermodynamics, we deal with the study of macroscopic property of a system at equilibrium. Essentially, we need to understand that we are studying the properties, macroscopic properties like temperature, volume, pressure at equilibrium. That means there is no change with time, using the laws governing the transformation of energy from one form to another. It does not concern with the microscopic variables that characterize individuals. When we say the microscopic variables, which is going to be characterizing an individual molecule, then what we deal with is the statistical thermodynamics. So, and basically, we should now go ahead and just recapitulate. I think most of you know what it is. What is a system, what's the surrounding, and what's the boundary? System is the part of the universe in which our interest of study, the property of which we are trying to study, that is situated. And surrounding is any area outside the region of the system from where we make the observations. And boundary is a hypothetical line between the system and the surrounding. System and surrounding together, what we nomenclate is the universe. And when we talk about a system, when we talk about a thermodynamic system, we generally categorize them into three: open, closed, and isolated, based on their boundary properties. Okay, so when we have an open system, what we have this is the diagram of an open system, where you have energy and matter transfer both possible between the system and the surrounding. That means essentially the wall should be dithermic. That means it should be thermally conducting and allow energy to pass through it. And the walls are rigid or maybe permeable. Based on that, what are the parameters we need to think when we are talking about equilibrium state? And that should become a non-variant and constant parameter. When we are talking about an open system, temperature and volume and chemical potential. Chemical potential is a term we are going to discuss when we are talking about open system. But right now we are going to be concentrating mostly on the closed system. Now, closed system, when we are talking about a closed system, you can see a closed system here where there is no matter transfer between system and surrounding, but there may be a transfer of energy. And if there is an energy transfer possible, that means the conducting wall is a diathermic wall. Okay, and as you can see, in open system, the boundary was permeable because it was allowing matter to transfer between the system and surrounding. But in a closed system, since matter is not allowed to transfer, so the wall is supposed to be impermeable. It can be rigid, it can be flexible, but it should be impermeable. So if they are impermeable and rigid, that rigid means the volume is fixed. So when we are talking about an equilibrium state, when we want to reach, what should be the condition which should be coming constant? Diathermal means you have to will have energy transfer so that the system and surrounding comes to a equilibrium, and that is why temperature is one thing which should be constant. Since it's a rigid volume wall, then what happens? Volume should be also constant, and the number of, since there is no transfer of matter, so the number of particles should be fixed. Now, this diathermal wall, if we have a flexible rigid wall instead of a rigid one, that means flexible means there is a pressure difference possible, and the flexibility is allowed so that the pressure is equalized. So when the pressure is equalized and there is impermeable because it's a closed system, then the parameters we should need to concentrate for equilibria becoming constant is temperature, pressure, and the number of particles. Now, the isolated system is an ideal system where you do not have any energy or mass transfer. That means the wall should be adiabatic, and it should be rigid, and it should be impermeable. So, opposite to open system, isolated system neither has an energy transfer or a matter transfer. So, the wall is rigid and also impermeable. So what is getting to be, whenever we are talking about a isolated system reaching equilibrium state, it is when the internal energy and the volume and the number of particles remain fixed, become constant. Okay, so these are the things which you should, I know these are not new things, but let us see for each of them, how does the system look like. Now, when you have an equilibrium, thermodynamic equilibrium reached, how can you distinguish that? When you have an isolated system, all the macroscopic properties come to a constant value, they do not change. They at equilibrium. When you have a non-isolated system, when it comes to equilibrium, when the macroscopic properties do not change with time, and if I remove one of the system from the contact with its surrounding, it does not cause any change in the properties of the system. So these are the criteria which we are going to be looking at when we are saying the equilibrium is reached. A system is in thermodynamic equilibrium is known as an equilibrium system. Now, the thermodynamic state can be decided whether it is going to be reaching the equilibrium or not is decided by the present values of the state variables and not on the history. So what are the conditions of the equilibrium and what should be satisfied to reach the equilibrium? So for that, let us look at this. You have a thermal equilibrium, you can have a mechanical equilibrium, you can have a material equilibrium. Material equilibrium comes in only when you have a open system, right? Mechanical equilibrium and thermal equilibrium can be associated with, say, whenever you have a temperature difference between the system and the surrounding, and this is system and surrounding, or two systems brought close together are separated by a diathermic wall. When there is a diathermic wall, there is a possibility of energy transfer. So if there is an energy transfer, it's a closed system. We are not talking about matter transfer. So it's a closed system condition where the equilibrium state is reached when the thermal equilibrium is reached. Thermal equilibrium means the system undergoes a change and comes to a condition where the temperature of the two system and the surrounding or two systems in contact become having the same temperature. What about the mechanical equilibrium? Mechanical equilibrium is where the boundary wall is flexible. When it's flexible, that means if I have a area which is marked like this, which is a high pressure area, then if this side is supposed to be a low pressure area, when they are both in contact, then the movable piston should move in such a manner that the pressure equilibrium is reached in either sides. No further change in pressure in either of the two conditions takes place. When you have an opposite system, then we had said that the wall between the system and surrounding should be porous or permeable, and the boundary should be dithermal. That means you have an energy transfer and you also have a mass transfer. Energy transfer should be such that on reaching the equilibrium state, the system and the surrounding, or the two systems in contact, have become the same temperature. And what about the mass transfer? Mass transfer will also again flow from a high concentration to a low concentration through the permeable membrane, so that you reach a concentration which is equal in both the system and the surrounding, or the two systems in contact. When we say a thermodynamic equilibrium is reached, when all of the three equilibria is present. Okay, so now to summarize, what is the thermal equilibrium, what is the mechanical equilibrium, and what is material equilibrium? This is the gist of what we just now discussed. Thermal equilibrium, it's a condition in which there is no change in the properties of the system and the surrounding when they are separated by a thermally conducting wall or a diathermic wall, a condition in which no change of state occurs when two adjacent objects or systems A and B are in contact through a diathermic boundary. Okay, so there is no change which is occurring, no change in state is occurring, they come to an equilibrium state. No further change is going to occur. When we have a mechanical equilibrium, there is no change in the properties of the system and the surrounding when they are separated by a movable boundary or movable wall. A condition of equal pressure in either side of the movable wall is a requirement. No unbalanced force acts on them or within them, and system does not undergo any acceleration or turbulence. When you have a material equilibrium, the condition is such that the equality in concentration of the species, whichever we are dealing with, the molecules, is in the various parts of the system is same with time, does not change. And there is no further transfer possible of matter from one region to the other, from one system to surrounding, or two systems in contact through a porous boundary. So this is the criteria for thermal equilibrium. For equilibrium. Now we said thermal equilibrium, we said mechanical equilibrium, we have said material equilibrium. But we had, when the laws of thermodynamics were established, there was no criteria for temperature. Temperature concept came much later. And since first law, second law was already established by then, so the new law, which was formulated for bringing in the concept of temperature, was called as the 0th law. Temperature is a property associated with the random movement of the molecules in the system. So the concept of temperature in thermodynamics is based on 0th law, and the idea of the concept of thermometer, a device for measuring the temperature, was introduced. What does the 0th law state? 0th law states that if I have a system A and a system B, which is connected through a diathermic wall, or they are in thermal equilibrium, and B is again in thermal equilibrium with C, then what happens? Then eventually we see that A will be in thermal equilibrium with C. So what is the thing which is happening? So all A, B, C are in the same temperature, but here what you see, B is in equilibrium with A and B is in equilibrium with C. So when we are saying A is equilibrium with B and C is in equilibrium with B, so B is acting as the thermometer. So thermometer concept is devised based on the 0th law. So a well-defined quantity called temperature exists such that the system two systems in thermal equilibrium is possible if and only if the temperature of the two systems are same. Okay, so after discussing the concept of temperature, which is briefly done, I did not go into the detail of it, how it was established. Now let us go into the thermodynamic state. How do you define a thermodynamic state? Thermodynamic state is a state of the system for which a fixed value of macroscopic properties are defined. Suppose I have a state, that state will have a definite value of certain thermodynamic variables like temperature, volume, pressure. That has to be fixed. These macroscopic properties that characterize the system, the thermodynamic variables, have to define the thermodynamic state. So how many thermodynamic parameters do we know, and what are the experimental measurables? Composition is one experimental measurable. Mass of each of the species present in the system or in a phase can be found out. Pressure, volume, temperature, density, these are also measurable thermodynamic parameters or variables. Field strength, magnetic field, electric field, which is acting on the system, is also thermodynamic variables, which are properties which we can think about. On the other hand, if you have a micro state of a system, like if you talk about statistical thermodynamics, that needs a description of each of the molecule. And the picture is a slightly complicated one, because you have to deal with each of the molecules, and whenever we are dealing with molecules, you have a number of particles, 10 to the power 23s, okay, Avogadro's number. So we are only going to be dealing with the macroscopic system, and this macroscopic systems, if it needs to be defined, definitely defined for a particular state, then how many parameters do we require? And what are these parameters going to depend on? These parameters are properties or parameters, whichever you can say. They can be of two types. They can be intensive and they can be extensive. Intensive thermodynamic properties, they do not depend on the size, quantity, amount of the matter present in the system. Okay, like pressure, temperature, viscosity, density. Temperature is a part, its characteristics or attribute of a system. It does not depend on the mass of the system or the size of the system. Viscosity also same. I wanted to know whether you know that whether pressure is what is pressure? Pressure is force by area. Force is what? Mass into acceleration, so it's mass dependent. And denominator is what? Area. It's again on volume dependent, mass dependent. But so the ratio of the two becomes an intensive parameter or intensive thermodynamic property. So ratio of two extensive properties become an intensive property. What is the extensive property? That is depending on the size. And the property is such that the total property of the thermodynamic property of the system will be such that if you add the component all throughout the system, if you consider small parts and if you consider the volumes of each of this part, the total volume of the system is going to be the summation of the volumes of each of the components which you have divided. So volume, number of moles, these are the two things which we can think about is an extensive property. We are going to deal with more extensive properties in the eventual classes, but for measurable ones, volume and number of moles can be taken. Other variables can be there: surface area, electrical and magnetic strength. These are all parameters which can be which are existing, but we are not going to take up in our discussion right now, though electric field will be something which we are going to discuss when we are talking about electrochemistry. So the homogeneous system, the system can be homogeneous, it can be heterogeneous. What is a homogeneous system? A homogeneous system is a system which is having its intensive macroscopic property uniform throughout in the system. That means you can visualize it as a single phase pure solution or a pure substance. The intensive macroscopic properties are uniform throughout the system. Only then a system becomes a homogeneous system. Okay, and if it is not, if it is not homogeneous, the macroscopic properties are not homogeneous throughout the system, then we get a heterogeneous system. So suppose you have water and benzene, they are not miscible. So you water and say acetone, they are not miscible. Even acetone is miscible. Let us say petroleum ether and water, they don't miss. So they becomes two phases, and they become heterogeneous system. So now we have talked about the thermodynamic parameters, the intensive, extensive, what a homogeneous system and a heterogeneous system is. Now, tell me how many parameters are going to be required to define a thermodynamic state. Like suppose you want to identify a person, like if a student of IIT Kharagpur, I want to identify that student. The basic minimum information, if I get the roll number, I can pinpoint the guy or the girl. If I don't know the roll number, I know which year he is, which department he belongs to. But if I want to add more attributes to finding him out, then I need two more additional things. I need maybe the hall in which he resides, and additionally his name. If I get these three criteria, his roll number, his hall, and his name, then I can go and figure out who this person is. Similarly, what are the minimum thermodynamic parameters which can identify a thermodynamic state? We can say this state is in this condition. Because of this, what are the thermodynamic parameters associated? So here, state of a thermodynamic system can be defined by a set of thermodynamic parameters. In fact, the macroscopic state of the system can be completely defined by these small sets of macroscope. You don't need all of them. You need few of them. Like I said, if a student information is required, I want to identify the system. I can find out what the name of the parents are, what his JE rank was, from which state he belongs. But I do not need all of them to specify or find out which the person is. Similarly, to identify a macroscopic state, I need only few variables to pinpoint the state exactly. Okay, and these parameters, for instance, the thermodynamic state of a single phase system of fixed amount of non-reactant substance can be described by two or three of the thermodynamic parameters like pressure, volume, and temperature. Okay, so the equation of state is the equation of what is the why is equation of state important? You know the gas law, PV equal to nRT. This is the equation of state. Equation of state is an equation that interrelates the various thermodynamic measurable properties. Okay, so that this is the equation of state is a parameter by which it reduces the number of variables I require to identify a state, the macroscopic state of a system. Okay, so let us see how many parameters we require. The state change in state depends only on the final and initial state of the thermodynamic property. It's independent of the path through which it's executed. It's a parameter, a system is going from one state to another, and maybe going up in a cyclic process, or maybe going straight towards the second point. But what I need to know, what is the initial and the final? The difference of final minus the initial value of the state corresponds to the change in state. I did not bother about through which path it executed while doing the process of going from state 1 to state 2. So how many basic parameters, thermodynamic variables or parameters we require to describe a macroscopic state? Only 3. If I deal with ideal gases, I require only 3 out of the 4 variables: temperature, pressure, volume, and number of moles of the species or amount of the species. Okay. If I have a single phase non-reacting gas, then I need only 3 thermodynamic parameters from the 4: temperature, volume, and amount of species need to be specified to describe the state. Only 3 of these variables need to be specified, while the 4th variable can be calculated from an equation of state. So you understand the equation of state, the importance of it. When I'm dealing with an ideal gas, then I can use PV equal to nRT. If I have 2 or 3 of the parameters known, if I have a parameter temperature, pressure, and number of moles known to me, I can find out the volume using the equation of state from the equation PV equal to nRT. Suppose a thermodynamic system of a specific amount of pure substance, okay, single phase, homogeneous phase, that means pure substance, and specific amount. Amount is known. Then how many variables are required to define that state? Since the amount is fixed, it's a pure state, then what do you require? Now from all these 4 variables, I now require only 2. For defining a state in a fluid state, the thermodynamic state of a fluid system can be described by only 2 of the 4 parameters. One of them being fixed. The number of moles gets fixed. So only now 2 will be required out of the 3 PV and T. When the amount of this substance is fixed, then either temperature, pressure, or pressure or volume, or temperature or volume are required. The 3rd variable can be calculated from the equation of state. When all the thermodynamic variables get fixed, then the system is supposed to be at an equilibrium state. So therefore, more variables need not be specified. We need to know the basic parameters to specifically pinpoint the state. More variables have to be specified to describe thermodynamic state of homogeneous mixtures of different species, because here we have taken species to be 1. So it is reducing the number of species, the variables which is associated. So the moles of all the species need not be taken into account. If the number of moles, different species are present, then the number of moles of, suppose A, B, C are present, then the number of moles of A and B and C need to be specified. So if I have a pure system and I have a specific amount, then only 2 out of 3 of the variables are required, and the other gets fixed by the equation of state. So therefore, for describing a state, thermodynamic state of a system, few experimental measurable macroscopic properties are required. Knowledge of if the system is homogeneous or heterogeneous is required. Knowledge if the system is in equilibrium state or not is required. And knowledge of number of components present in the system is required. An equation of state is a device or a methodology which is going to ease our process in identifying the number of thermodynamic properties required to describe a particular thermodynamic state. The equation of state relates the macroscopic variables of a given substance in the thermodynamics equilibrium. Okay, so this is the geometrical representation of equation of state. A function of PVT equal to 0. The equation of state and ideal gas is, as you know, is PV equal to nRT. Now, if you look at this diagram, you have temperature, you have volume, you have pressure axes. Now, if I want to, if I look at this point, the dot I have drawn, this signifies one equilibrium state for which the P, V, and T is fixed. Now I can generate a number of points on this area for which I can identify and fix the temperature, pressure, and volume. So a region of PVT surface of fixed amount of gas can be projected, and this is representing the projection of the surface which can be generated. See, I have this point, I have this point, I have this point. If I have continuously points all over, then I can generate a surface for which the system is in equilibrium. Okay. So I'm not going to go into the mathematical representation of this. PV equal to nRT. You have van der Waals equation, which is a modification for volume correction and non-intermolecular interactions. So we have this introduced volume correction and the interaction factor. So here you see I have this. How was this Boyle's the inert law derived? It was from the Boyle's law, Charles' law, and the combination of Avogadro's law. So I'm not going to discuss this here, but just for your reference, what does a pressure temperature curve look like? Pressure temperature curve is going to be linearly proportional. Pressure is proportional to T according to Boyle's law. You have pressure inversely proportional to V. So we have a plot like this. And here what is, when you plot pressure against temperature, what is fixed? Fixed is the volume. So volume being fixed, each of these parameters corresponding to these lines correspond to different volume. Similarly, when you plot according to Boyle's law, each of these lines corresponding to different temperatures. And similarly, if you plot volume versus temperature, each of these lines corresponding to a given value of pressure. So this is isobaric plot, pressure is constant. This is isochoric plot, and this is isothermal plot. Clear? Now, before we go into the details of it, I would like to give you some fundamental insight into the partial differential, though it's not my subject or my specialization, but we need to know some things. If suppose there is a function which is dependent on two variables, then the partial derivative of that function is given by the rate of change of that function with respect to one variable with the other variable left remaining constant. If you can see this, you are differentiating the function with respect to x. Suppose a function is function of x and y. You differentiate with respect to x, keeping y constant, and then you put the differential. How do you represent the differential? Delta change in x, fx with delta change in x minus fx y divided by the change in delta x. So this is what the within the limits of delta x tending to 0, this is how you represent the differential. Similarly, the function should be can be differentiated with respect to the other variable. Since it's a function of x and y, it should be differentiable with y, keeping x constant, and then see the change in the function with the incremental change in y minus the function with xy divided by the total change in y, limit tending to x, y, delta y tending to 0. So if I have something like this, have a look at this. I have a function of which is a function of x and y, x squared y. Then what does the differential of f with respect to x, y constant become? Do you differentiate with this? So it becomes 2xy. Now, if I have this function only differentiated with respect to y, then what do I get? I get with respect to, there is y here, so it becomes x square, right? So this is the partial differential, how you represent. The partial addition of the two partial differential should give you the total differential, and if it is possible or not, let us see. So if you have a first order differential, then we say the function, if it is a function of x and y, then the total change or total differential of the function f is given by the change in f with respect to x, keeping y constant, into the total change in x, plus how the function is changing with y, keeping x constant, into dy. Okay, this is the first derivative. And what is the second derivative? Second derivative is whatever you have here. Whatever you have here, the first derivative, if you differentiate this, whatever you get with that of the second variable, and if we can represent is like this, what you have is differentiate x with respect to f with respect to y, keeping x constant, then whatever you get, we differentiate with respect to x. How do you differentiate? How do you represent? This is how you represent. Okay. Similarly, if you had differentiated with respect to x first, then you whatever you get, you differentiate with respect to y, then you can write something like this. Okay. Now, for a function like this, you see the first differential was 2xy, we just now discussed, and the first differential with respect to y, keeping x constant, was this. So the function which can be total differential can be represented. Total differential can be represented as the first differential plus the dx, and the second differential, first differential of the second variable with dy. So if I write this, if I have this as the function, then what will be the total differential? Total differential will be 2xy into dx plus x square into dy, right? Now, if I have this differentiated with respect to x, keeping y constant, now I differentiate this with respect to y, keeping x constant, what do I get? If I differentiate with respect to y, keeping x constant, after I differentiate, I have already differentiated once, that's the first differential. Now I carry out the second differential. Whatever I get, that I differentiate with respect to y, keeping x constant. What do I get? I get 2x, x square. Sorry, where is it? Here. I get 2x. Okay. Similarly, if I have the first differential form, I say from this with respect to y, keeping x constant, it is x square. Now I differentiate this with respect to x, keeping y constant. So that's what we have done. What do you get? You get 2x. So you understand that for this sort of a function where the double differentials become equal, then we say it's an exact differential. See, this is the first differential we taken. This is the first differential for x, and this is the first differential with respect to y. Now, this with respect to x, I differentiate again, this time with respect to y, and this first differential with respect to y, I differentiate again with respect to x. Okay. So if I do that, the double differentials become equal, 2x and this, 2x and this. So this a function is known as the total differential, or perfect differential, or exact differential. Am I clear? So if I have to generally write an expression, if I write an expression of fxy, like f is a function of x and y, then what I can write, the total differential will be m, a function of xy into dx, plus n into xy into dy. So you can, if you identify this equation with this one, what does it represent? That represents that m is actually nothing but the differential of f with respect to x with keeping y constant. And what is n? N is nothing but differential of x with respect to y keeping x constant. Right? That is what we have. So the question is, would any expression like m a function of xy dx plus n function of xy dy will always represent the total differential of the function f? It will this form will represent the total differential of the function f only when the differential of this m differential with respect to y and n differential with respect to x becomes equal. That's what we had seen. These were double differentials were equal. So it became a perfect differential. So similarly, for any function to be represented as a total differential df, we can write it in terms of m, which is a function of xy dx, plus n, a function of xy dy, only if the differential of m with respect to y keeping x constant is equal to the differential of n with respect to x keeping y constant, which are, in other words, means the double differentials become equal. Okay, like the double differential we had taken, they become equal. Okay, only then we can represent that this d function df, which is representation of the partial derivatives of the two function x and y, is going to be giving the total differential, and that time we call it a perfect differential or exact differential. Let us see a few examples. Look at this. This is a function given to you. The differential function given to you. This is the differential function which is given to you. Can you identify what is going to be m and what is going to be n? M, if you remember the expression, m x xy, function of xy dx plus n function of xy dy. So if I identify, then 2xy is my m and n is x square. Okay. And what will be the double differentials of these? Please do it. These are things which you have to solve. So the function can be represented as, the function here can be represented as x square y. Can you tell me why? Why I can write this as x square y? Anyway, you think about it. I have given you two terms, the total differential form, and from this, how you will get the function. What is the function? How is the function going to be represented as total differential like this? Okay. Now, similarly, if I have a function like this, I have what my m is, what my n is, I can identify. So this, my, if whatever is associated with the dx is going to be m, whatever is associated with dy is going to be my y, n. So what is my m? It is 3x square y square. N is 2x to the power 3 y. So if I have to say that this form represents the total differential, how will I say? When the double differential of this becomes equal. So what happens if the double differentials are not equal? We call this an inexact differential. Expression of this total differential does not represent the total differential or exact differential when the double differential of m with respect to y, differential, second order differential of m with respect to y keeping x constant is not equal to differential of n with respect to x keeping y constant, where you remember m is nothing when the function with the initially the function is supposed to be dependent on two variables x and y. This is only the criteria you should remember. So if this is m function with respect to x keeping y constant, n is function differentiated with respect to y keeping x constant. Now let us see a few examples of the inexact. Inexact, suppose I have m equal to 1 and n equal to 0. What will the differential form look like? It is going to look like something here, m equal to y and y dy equal to n equal to 0. So it becomes 0 into this is not going to exist. So the function total differential becomes dz x dx, right? Y dx. This is m is y, so y dx. Similarly, if I have m equal to 0 and n equal to x, n equal to x here and x equal to 0, m equal to 0. So what you have? You have for the function total differential function is equal to x dy. Am I clear? From here you can see, you put in the plug in the m and n value in this and you will get the total differential f or total differential z. usually we do not write f, or you can write f, it's not wrong. You usually write a function z is a function of, f is usually represented for a function, so z is usually a function of x and y. That's how we write. So if I have another parameter, suppose I have m equal to x y into xy plus 1 and n equal to minus x. The total differential will become y into xy plus 1. This is if you compare, plug in the m here, and n is minus 1, so n is minus x, so minus x dy. These are examples of non-exact. If you differentiate with respect to x, you do not get the same. If you now m you differentiate with respect to y, what do you get? 1. N you cannot differentiate with respect to x, it's already 0. So 1 is 1 and other is 0. So here the double differentials are not equal. So these are examples of non-perfect differentials or inexact differential. Now, what are the properties which are associated? Let us point by point take up the properties. Integration of an exact differential. Let us say move from one point xi, yi initial point to a final point xf and yf. The change associated in the function xy, function of xy, can be represented as delta f or df. And when we write delta f, we are talking about a discrete change. So discrete change, if I can take, it will be the difference between the value of the function at the final state minus the value of the function at initial state. If I want to rewrite in terms of the differential, I can write a df from this is a continuous change and this was a discrete change. It's nothing. It will also give you a discrete change when you are integrating it from initial to the final. So if you are differentiating with respect to the function from initial to the final, what do you get? You get m dx plus n dy. This is what we are been saying all throughout, that total change in f is only dependent given by mx dx plus n dy integrated over initial to final state. The value of delta f, the total change in function from when it's undergoing a change in state from initial to the final, depends only on the values of x and y, values of the function at the initial and final. This is the initial value and this is the final value of the points only. It is independent of the path taken. It is taking from going from initial to the final. There is no information required for that. And since the initial and final points are the change in the state is given, the total differential of the parameter is going to be depending on the discrete change in the of the value of the property at the final minus the initial. Then if I have a cyclic process, closed process, then what happens? Closed process for the initial point becomes the final point. So over a cycle, if it is a state function or a perfect differential or exact differential, then over a cycle it should become 0. Over the cycle, if the differential of that function should become 0. Integration of an exact differential function df for a closed system or a cyclic process where the initial and the final states are equal is always going to be delta f integrated over a cycle equal to 0. This is how you represent. So few more things which you whatever we have just now discussed, it is few more things. If the integration integration of the differential form is along arbitrary path, simply the difference of the values of the function at two limits is to be taken, a to b. So total change in u is equal to change in the value of the function at final point minus the initial point. So such functions for which integration is path independent is an exact differential, and these functions are called as state functions. So whichever function is can be integrated over over the path over the change in state from the initial to the final, and is only the value which is the value of the property at final minus the initial, such a integral, such a function, integration of such a function, such functions are known as a state function. That means the total differential for that function is going to be a perfect differential. Okay. And if an integral of a differential of a function depends on the path that changes chosen to change go from one state to another, the differentials are called inexact. For example, you have this. For example, you have this a function differential of the function integrated over from initial state to final state. This should be equal to W, but this W is not equal to the discrete change of the value of W at final minus the initial. Such functions for which integral differential integral of the differential is path dependent, that means depending on how you carry out the change, and that is and is not a simple difference between the values of the function at the two limits, is an inexact differential, and it's a path variable or path function. Okay, another rule for a path function is, suppose I have a function z is dependent on x is dependent on say x is dependent on s, and y is dependent also on s, and fx is dependent on s. That means we can write down the Euler's rule as the total differential of whatever you get. The total differential whatever you get, you will differentiate with the second variable which you have generated. Initially it would have been dx into y into dx plus df dy x into dy. Now you are differentiating with respect to the s. So you are the total function you are differentiating with respect to a function s, and here it becomes dx ds, and here it becomes dy ds. Now, what is the chain rule? What does it say? Suppose you have a function v function of pressure and temperature, pressure a function of volume and temperature, and such like that. If they are interconnected, then what you can write? You can write in a cyclic order. In a cyclic order like this. If I start with pressure, pressure will be differentiated with respect to T at volume constant, and T will be differentiated with respect to V at pressure constant, and then V will be differentiated with respect to P as at T constant will be equal to -1. Take an assignment to do it to find out if I have to apply each of these differentials, P by T at constant volume, delta T by delta V at constant pressure, all of these value, calculate for an inert gas and show it that it comes to -1. Please do it, okay? Now, another important two terms I would have to wind up. Two terms, the sum of the properties of the inexact is the sum of two inexact differentials can become equal to an exact differential. Okay, so if suppose I have a function z prime is equal total differential of that function z prime is equal to y dx, is an inexact differential. And how do we give that z prime? Z prime is the area covered in green. That it's integration of the area from 1 to 2. The state is changing from 1 to 2, and the total differential of that integration of the total differential of that function z prime is nothing but the change of differential between x1 to x2 into y into dx, and that represents this area. Total differential in volume into the y. Okay. Now, in the case 2, suppose I have another function x double prime, which is a total differential of which can be represented as x dy. And this you can see and make out that this is also an inexact differential. Now, the area corresponding to this is the blue one, and the area corresponding to this is the green one. So, what do I have? I have two differential forms, sum of two inexact differential. This I say is inexact. This is also I say is inexact. So this is also inexact. This represents the area here, and this represents the area here. So when I add these two up, the sum of the two differential becomes equal to an exact differential. And a classic example of that is, I hope you remember that work and energy are path functions, but when we add work and internal energy, work and energy transfer Q, then it becomes equal to U, delta U, and delta U is a path function. So if you can look at this, the exact sum of the two integrals, two inexact differentials, if I sum it over, this is the third case when I have the function, the total differential of dxy, which is a exact differential. Now, if I do that, I can see that if I add up the differential of, say, this part and add up the differential of this part, integrated over x to x1 to x2, and here integrated over x1 to x. Sorry, this should be y. This should be y1 to y2. Okay, so this represents this area, this represents this area. So the total differential is nothing but, if you can simplify, it will be nothing but the sum of the two inexact thermodynamic parameters. Okay, the last one I want to emphasize that if you have an inexact differential, if you multiply the inexact differential, which we will see in when we talk about entropy, if you multiply the inexact differential with the appropriate integrating factor, then it becomes an exact differential or perfect differential. So if I have an inexact differential in the form of like this, and if I have an integral factor tau, which is nothing but 1 by y square, thus what we can write that the total differential of z with respect to y square is equal to x plus 1 by y into dx plus or minus x by y square into dy. Just plug in in that equation. Okay, so let us see this. If you differentiate this, I have done it in a elaborate manner. So here you see, this is my total function. This is my total function. So this total function is, if I want to find out what is my m is nothing but this one into dx, and what is n is nothing but minus x minus 1 minus x. So if I want to find out the total differential of whether it's inexact or exact, I differentiate m with respect to x, keeping y constant. What is going to that become? What is going to that become? This is x's first term is x's x y square plus 1, x y square plus 1. If I differentiate with respect to y x, then what do I get? I get 2xy plus 1. But if I differentiate this with respect to x, the y, sorry, x with keeping y constant, then what do I get? I get minus 1. So the double differentials are not equal. So this being not equal, but it if I multiply the function now with 1 by z y square, then multiplying the integrating factor with the given function we get, what do we get? This was the function which you remember. This was written like this. So this is nothing but x plus 1 by y dx. I want you to figure out how it's happened. X equal to fx equal to total differential divided by with respect to y square, and that is equal to m by plus 1 by y into dx, and পরেরটা তো তুমি খেয়ে নেবে। sorry so we have this m here. If I differentiate with respect to x now, what do I get? And if I differentiate with n with respect to y now, n with respect to x now, and y with respect to m with respect to y now. Yeah, m with respect to y, x keeping x constant, n with respect to x, y constant. What do I get? Both the places I get 1 by minus 1 by y square. So here you can see, by multiplying the function with 1 by y square, I could generate an inexact form to an exact differential, and function can be written something like this. Integrating factors are useful for obtaining the exact differential from the inexact differential form and in solving first order equations. So this is to summarize. This is to summarize what we have done so far. So what we have taken, if we have a function z, which is a function of x and y, the total differential of that function z is given to be how the z is changing with respect to x, keeping y constant, into the total change in x, plus how the z is changing with y, keeping x constant, dy. And if I represent this part as m and this part as n, then I can write down the total differential as m dx plus n dy. The condition for exactness is when m is differentiated with respect to y, keeping x constant, and n is differentiated with respect to x, keeping y constant, you should be having them equal. If the double differentials are equal, then the function is supposed to be a state function. Z, again, it's delta z, the total differential, will be a perfect differential when it has the following. Dz is a unique value function, depends entirely on the instantaneous value of x and y. Dz between two specified points or states is independent of the path through which the transition is taking place. Dz for a complete cycle is supposed to be 0. If we have not discussed the first law as yet, but I know all of you know. So the change in dq and the change in exchange in energy, that means dq, and dw, the work done, are inexact differential, but when they are added, they become equal to a change in internal energy, and that is that's the state function. So I would like you to do this. These are assignments which is to show each of the factors can be written in terms of the partial differential. This is very important that you practice, because the entire thermodynamics is standing on this. If it is v is a function of p and t, how will you write down the total differential? If p is a function of v and t, how you write down the total differential? Similarly, like this, show for an ideal gas the change double differential of temperature with respect to volume and pressure is equal to the change in ddt divided by dv dp equal to 1 by r. Please show this. Please show this. And we are going to introduce two terms. The response function, one is the volume increase with the temperature, is the expansion coefficient, which is given by the change in volume with respect to temperature at constant pressure. So that is why when you apply temperature, a system is supposed to undergo expansion, and when the pressure is held constant, so we call this a function, a parameter which is baric expansion coefficient, which is represented by alpha. 1 by V is the total change in V into the change in V with temperature at pressure. Another term is another response function is how fast the fraction of volume is increasing or decreasing is obtained from this. How fast the fraction of volume decreases when we apply pressure. This gives a parameter kappa T, and that kappa T is nothing but the change in function, the change in volume with respect to pressure at constant temperature into 1 by V, the total change. And we have a negative sign because there is a decrease in volume taking place. So I think I'll end it here. I'll take up the state function examples in the next class. Thank you.